Okay, so we've learned a lot about vectors. We know how to add vectors, how to subtract vectors. We know how to express vectors in terms of components. And now we're going to learn another mathematical operation that we can perform with vectors, which is called the scalar product, and often more commonly known as the dot product, and you'll see why in a moment. So here's the mathematical formula for the scalar product. First, in terms of notation, we're going to start with one vector A, I'm going to have a dot, a large circular dot, and vector b. So that's the notation that tells you, okay, we're calculating the scalar product. And how do we calculate that? Well, we take the magnitude of a, right, multiply by the magnitude of b, and then we multiply that by the cosine of the angle between two vectors. Right, so when we're calculating the scalar product, we want to always draw our vectors like we do here, with the tail of A and the tail of B touching, so that this angle phi is the angle between those two vectors. Okay, and so this isn't so hard to calculate, and it's going to give you a number, right? A number, and that's why we call this a scalar product. It returns a number, not a vector. Okay, it turns out there's another separate definition for the scalar product, which gives you an equivalent answer. It's just another way of calculating it, and that's up here on the right. So I take the x component of my vector A, multiply that by the x component of my vector B, and add to that ay, by, and add to that az, bz. All right, so that is an equivalent definition. This way we calculate it using the components of the vector. In this method we use the magnitude of the vectors and the angle between them. Okay. Okay, so that's a scalar product. Let's conceptually try to understand it a little bit more. I have these two vectors, a and b. The dot product returns a number which is equal to the lengths of a multiplied by the component of b, which is parallel to a. Okay, so let's try to understand what I mean by that. If I look at the equation for the scalar product, I have the magnitude of a, right? So that's just the lengths of this vector. Right? That's just some number equal to the lengths of vector a. Multiply that by the lengths of vector b times the cosine of the angle phi between a and b. And if I look at these two vectors drawn tail to tail, and I do what's called projecting b onto a, that is, looking at my vector b and then dropping down a line from b to a such that that line is perpendicular to a, right? This is a 90-degree angle here. You can kind of imagine that a flashlight is up here and you're shining a flashlight down, and this is the length of the shadow cast by that flashlight. Right? So I have this triangle, and I have a component of that triangle which is adjacent to this angle, and that adjacent angle, that adjacent side of the triangle I can always figure out using a cosine. Right? So it turns out this length of b projected onto a is b cosine phi. So the component of b, which is parallel to a, is given by b cosine phi. Okay, so that's what this equation is doing. It's just multiplying the length of a by the component of b, which points along a. All right, so that's what this orange line is here. Okay. Now, even more conceptually, the scalar product is telling us a measurement of how parallel two vectors are. So it's going to be largest when two vectors are parallel, and smallest, or it's going to be equal to 0 when two vectors are 90 degrees apart. Okay, it's actually also going to tell us when two vectors are anti-parallel, it's going to be negative in that case. We'll talk about that more on the next slide. But let's just check this out. So in the first example, we have two vectors a and b, and they're parallel to each other. So if I was to calculate their scalar product using this formula, it's just the length of a times the length of b times the cosine of the angle between them. The angle between them is 0, they're pointing in the same direction. And we know that the cosine of 0 is equal to 1. Right? So that's the biggest a cosine can be. Right? Cosine will always return something between 1 and negative 1. So the biggest it can be is equal to 1. So the largest the scalar product of these vectors is going to be is when they're parallel to each other. Right, so in this case, when they're parallel, the dot product is the biggest it can be. Okay, let's check a different example. Let's say a and b are separated by 60 degrees. Right? I still take the magnitude of a multiplied by the magnitude of b, but this time I take cosine of the angle between them. I do cosine of 60 degrees, and that's equal to 1/2, or 0.5. Right, so the dot product of these two vectors is going to be smaller than the dot product of these two vectors, even though, even if they had the same magnitude, the dot product would be smaller, right? Because the cosine of this angle would be 1/2. Right? So the dot product gets smaller as this angle gets bigger. Okay. Finally, if I calculate the dot product for two vectors which are perpendicular to each other, when I do cosine of the angle between them, cosine of 90 degrees is 0, right? So in this case, these vectors aren't parallel at all. There's no component of B which is parallel to A, so therefore the dot product is 0. Right? So you can kind of see that the dot product or the scalar product tells you, how parallel two vectors are. Okay. It also can tell you about if they're antiparallel or not. Right? So if I have these two vectors, A and B, and I calculate their scalar product, I plug in the angle between these two vectors, which is 180 degrees. Cosine of 180 degrees is -1. Right? So that's kind of the smallest a dot product can be, is when two vectors are antiparallel. Right? That's the most negative that dot product is going to be. In this example on the right here, B is now separated by A from 100 with a 120 degree angle. Right? So B has some component which is perpendicular to A and some component which is parallel to A, and that component parallel to A is really antiparallel. Right? It's pointing in the opposite direction of A. That's the little orange line here. Right? So in this case, the cosine of the angle is cosine of 120 degrees is -0.5. So this is telling us that B has some component which is antiparallel to A, but it's not completely antiparallel to A. All right, so that gives us some idea of the mathematical reason for defining the scalar product. Now let's talk about why are we using the scalar product in physics? Why is this kind of weird mathematical definition useful to us in a physics context? And the example I like to always use is pulling a train. The scalar product is a mathematical method we can use to compute useful work. So when we get many chapters from now define things like work and energy, it turns out we're going to have to use the scalar product to define a real physical observation about an example like pulling a train, okay, and calculating something called work. So we have this guy who's trying to pull this train down the tracks. And if this person pulls the train directly in the direction the train is moving, all right, all of your effort is useful. All right, if I'm pulling the train directly down the track and the train is moving down those tracks, all of my work that I'm doing is useful work, and I'm helping to move that train. Right, I'm going to speed up that train as I pull in that direction. Right, where if you were going to pull at an angle, right, you'd have some component of your force would be in the direction the train was traveling along the tracks. So that purple component here would help move the train, but there's also a component of this force vector in this direction perpendicular to the train, which is wasted work, right? That force is not doing anything useful, right? So the scalar product would help us to calculate this component of the force, which is doing the useful work, okay? And a couple extra examples here, as we talked about, when I have two vectors, say I have the force vector and I have a displacement vector here, the scalar product is going to be the biggest it can be, right, because these two vectors are parallel, right? Likewise, if I have these two vectors, the orange and the black here, a force vector and a displacement vector, if I calculate the dot product of these two vectors, I'm going to get a smaller number than I did here, right, because it's only a component of the orange force, which is along the displacement, right? It's just the purple. So this is going to be a smaller amount of work than this. It's going to be less useful, right? If I pull 90 degrees from the direction the train is traveling, I'm not doing any work. I'm not doing anything useful. It may seem like I'm doing work, but I'm not helping to speed up or slow down the train. So in our eventual physics definition of work, that's going to be zero work, even though you're applying a lot of force. But your force is wasted. It's not being used to pull the train. And in this case, I have a component of my force which is opposite the direction the train is traveling. So that's going to help slow down the train, right? So this is going to be what we call negative work when we get to that chapter. And anytime you have a scalar product which is negative, that's going to slow something down in this case. So I hope that gives you some idea of why we need to define this mathematical context, mathematical definition of the scalar product. One quick side note on the scalar product, we have these two definitions. We talked about the magnitude of A times the magnitude of B times the cosine of the angle between them. We also have the definition that includes the components of the vectors. In most cases, this is going to be more useful to you because we often define vectors with their components. We often write down a vector A in terms of its x component, I hat plus y component j hat plus z component k hat. So therefore we can just read off the components of our vectors and plug them into this equation, and that'll be useful for us for calculating the scalar product. Where if we wanted to use this definition, we'd have to do some trig to figure out the angle between them, and we'd have to figure out the magnitudes. So that would be maybe a little bit more of an effort. In other cases, you may have a problem where they tell you the magnitudes and the angle, and this would be the easier formula to use. Right? But if they tell you the components, right, tell me this is vector A, it has this x component and this y component, I'm just going to multiply this x component times this b component of b in the x direction and add to that this component of A in the y direction times this component of b in the y direction, and that's going to give me my scalar product. Okay, and then that brings us to kind of the final reason why the scalar product is really useful. We're going to use it when calculating real physical quantities like work, but it's also very useful in any mathematical context for finding the angle between two vectors. Right? If I look at this formula, if I can compute the right-hand side of the formula and get some number, and then if I know the components, it's pretty easy for me to calculate the magnitudes. So I could find a magnitude of A, magnitude of B relatively easily, and I could solve for cosine of phi. I could solve for the angle, right? So here I've written that out for you. I've solved this equation up here for phi, and cosine of phi is just A dot B, or writing out in terms of components, AX BX plus AY BY plus AZ BZ, and then just dividing by the magnitude of the two vectors multiplied together. Right? And it's pretty easy to calculate the magnitude of a vector with our magnitude formula. So this is a really nice way to calculate the angle between two vectors. In 2 dimensions, calculating this angle would have been a little bit of work. I would have probably had to figure out, this angle and figure out, this angle, and I would have to subtract those. In 3 dimensions, if I draw 2 random vectors, it becomes a lot of trig if you want to figure out the angle between them. But this definition is going to be really easy to calculate the angle between 2 vectors. So it's a really useful thing to use, and if you were using vectors, say as a computer programmer, programming vectors in a video game or something like that, you would probably use this all the time to calculate the angle between 2 vectors. So on to the next video.